Right, so hello and welcome back. This time we start with Smart Society and AI. The last time we finished with the foundation. We also finished with the history of artificial intelligence. And this time it's time to see what we see about the data. So the role of the data in AI. That is, seeing data as a universal resource, obtaining and manipulating data, looking for mistruths in data, defining data acquisition limits, and considering data security as well. So there is nothing new about data. Every interesting applications ever written for a computer has data associated with it. Data comes in many forms, some organized, some not. What has changed is the amount of data. Some people find it almost terrifying that we now have access to so much data that details nearly every aspect of most people's lives, sometimes to a level that even the person doesn't realize. In addition, the use of advanced hardware and improvements in algorithms make data now the universal resource of AI. To work with data, you must first obtain it. Today, data is collected in manually, as done in the past, then also automatically using new methods. Collection methods take place on a continuum from fully manual to fully automatic. You may find a focus today on collecting this data ethically. Now, in this chapter, we explore issues surrounding data collection. Raw data doesn't usually work well for analysis purposes, and this chapter also helps you understand the need for manipulating and shaping and structuring the data so that it meets specific requirements to be able to analyze that and to pull out information from that. You also discover the need to define the truth value of the data to ensure the analysis outcomes match the goals set for applications in the first place. Interestingly, you also have data acquisition limits to deal with. No technology currently exists for grabbing thoughts from someone's mind as telepathic means. Of course, other limits also exist as well. It also doesn't pay to collect data in a manner that isn't secure. The data must be free of bias, uncorrupted, and from a source you know. Now let's see about finding data ubiquitous in this age. Big data is more than just a buzz phrase used by vendors to propose new ways to store data and analyze it. The big data revolution is an everyday reality and a driving force of our times. You may have heard big data mentioned in many specialized scientific and business publications. And you may have even wondered what the term really means. From a technical perspective, so here you see, big data refers to a large and complex amount of computer data, an extremely large one, and complex data sets that cannot be processed by traditional methods. Big data implies a revolution in data storage and manipulation. It impacts what you can achieve with data in more qualitative terms, meaning that in addition to doing more, you can perform tasks better. From a human perspective, computers store big data in different data formats, such as database files like a CSV, or data structuring XMLs. But regardless of the storage type, the computer still sees data as a stream of ones and zeros, the core language of the data, or the computer as well. You can view data as being one of two types, structured and unstructured, depending on how you produce and consume the data itself. Some data has a clear structure, so you know exactly what it contains and where to find every piece of data. Other data is unstructured. You have an idea of how it contains, but you don't know exactly how it is arranged, how it is organized. Typical examples of structured data are database tables, spreadsheets, in which information is already arranged in a column and a row shape, so in a tabularized form. And each column contains a specific type of information. Data is often structured by design. You gather it selectively and record it in its correct place. Now, for example, you might want to place a count of the number of people buying a certain product in a specific column, in a specific table, or in a specific database. As with a library, if you know what the data you need, you can find it immediately. In the case of unstructured data, well, this data consists of images, videos, and sound recordings usually. You may use an unstructured form for text so that you can tag it with characteristics such as size, date, or content type. Usually you don't know exactly where data appears in an unstructured data set, because a data appears as sequences of ones and zeros that an application must interpret or visualize. Transforming unstructured data into a structured form can cost a lot of time and effort and source, and can involve the work of many people. Most of the data of the big data revolution is unstructured and stored as is, unless someone renders it structured. So first, this big data must be structured. This copious and sophisticated data store didn't appear suddenly overnight. It took time to develop the technology to store this amount of data. In addition, it took time to spread the technology that generates and delivers the data, namely computers, sensors, smart mobile phones, the internet itself, and also SNS, etc. The following section, so now we can continue talking about the using of data everywhere. Scientists need more powerful computers than the average people because of their scientific experiments. They began dealing with impressive amounts of data years before anyone coined the term big data. At that point, the internet wasn't producing the vast sums of data that it does today. The big data isn't a fad created by software and hardware vendors, but has a basis in many scientific fields such as astronomy, so space missions as well, satellites, so surveillance and monitoring, meteorology, physics, like particle accelerations, and genomics, so DNA sequences. Also, an AI application can specialize in scientific fields such as IBM's Watson, which boasts an impressive medical diagnosis capability because it can learn information from millions of scientific papers on diseases. The actual AI application driver often has more mundane facets. Actual AI applications are mostly prized for being able to recognize objects, move along paths, or understand what people say and speak to them. Data contribution to the actual AI renaissance that molded it in such a fashion didn't derive from the classical source of scientific data. The internet now generates and distributes new data in very large amounts. Our current daily data production is estimated to amount to about 2.5 quintillion bytes. So quintillion means 18 zeros. With the lion's share going to unstructured data like video and audio. All this data is related to common human activities, feelings, experiences, and relations. Roaming through this data, an AI can easily learn how reasoning and acting more human-like works. So let's see a few of the examples of more interesting data you can find. The first one is a large repositories of faces and expressions from photos and videos posted on social media websites like Facebook, YouTube, Google, Instagram, and they provide information about gender, age, feelings, and possibly sexual orientation, political orientation, or IQ numbers as well. Then the next one, the second one, would be privately held medical information and biometric data from smartwatches, which measure body data such as temperature and heart rate during both illness and good health. Interestingly enough, data from smartwatches is seen as a method to detect serious diseases such as COVID-19 early. The next one, so number 3, is about data sets of how people relate to each other and what drives their interest from sources such as social media and search engines. For instance, a study from Cambridge University's Psychometrics Center claims that Facebook interactions contain a lot of data about intimate relationships. And fourth, the last one, information on how we speak, which is recorded by mobile phones. In this case, let's say, OK Google, a function found on Android mobile phones routinely records questions and sometimes even more, as explains in Google's been quietly recording your voice as well. So this happens not just in the case of Google, but also in the case of Apple. Every day, users connect even more devices to the internet that start storing new personal data. There are now personal assistants that sit in our houses like Amazon Echo and other integrated smart home devices which can be regulated by our voices. These are just at the tip of the iceberg because many other common tools of everyday life are becoming interconnected and able to process, record, and transmit data. And the IoT itself now is about becoming full reality. So we continue now with putting algorithms into action. The human race is now at an incredible apex of unprecedented volumes of data generated by increasingly smaller and more powerful hardware. The data is also increasingly processed and analyzed by the same computers that the process have spread and developed. This statement may seem obvious, but data has become so ubiquitous that its value no longer resides only in the information it contains, but rather in its use as a means to create new values. Some people call such data the new oil. These new values exist mostly in how applications manufacture, store, and retrieve data, and in how you actually use this data by means of smart algorithms. Algorithms and AI change the data game as well. AI algorithms have tried various approaches along the way in the following order: simple algorithm, symbolic reasoning based on logic, and expert systems. And now we are at the neural network and deep learning. In recent years, algorithms have moved to neural networks and, as I mentioned, deep learning. As this methodological passage happened, the data turned what molded the algorithm into something useful for the task. Data turned from being just the raw material that fueled the solution to the artisan of the solution itself. Thus, a photo of your kittens has become increasingly useful, not simply because of its effective value, but also because it could become part of the learning process of an AI discovering more general concepts such as which characteristics denote a cat or understanding what defines cute. On a large scale, a company like Google feeds its algorithms from freely available data such as the content of websites or the text found in publicly available texts and books. Google Spider software crawls the web, jumping from website to website and retrieving web pages with their content or text and images. Even if Google gives back part of the data to users such as search results, it extracts other kinds of information from the data using its AI algorithms, which learn from its how achieve other objectives. Algorithms that process words can help Google AI systems understand and anticipate your needs even when you are expressing them not in a set of keywords but in a plain, unclear, natural language, the language we actually speak every day. If you currently try to pose questions, not just chain of keywords, to the Google search engine, you notice that it tends to answer correctly. Since 2012, with the introduction of Hummingbird update, Google has steadily become better able to understand synonyms and concepts, a strategy that goes beyond the initial data it acquired, and this is the result of an AI process. A few years after Hummingbird, Google deployed an even more advanced algorithm named RankBrain, which learns directly from millions of queries every day and can answer ambiguous or even unclear search queries, even expressed in slang or colloquial terms, or simply riddled with errors. RankBrain doesn't service all the queries, but it learns from data how to better answer queries. Let's continue with using data successfully, which is our next part. Oh, here, actually, I just added the slides as well related to these things. So, using data successfully. Having plentiful data available isn't enough to create a successful AI. Presently, an AI algorithm can't extract information directly from raw material or raw data. Most algorithms rely on external collection and manipulation prior to analysis. When an algorithm collects useful information, it may not represent the right information. The following part, which we handle now, will help you to understand how to collect, manipulate, and automate data collection quickly. Well, the next one is this time considering the data sources. The data you use comes from a number of sources. The most common data source is from information entered by humans at some point, you see here. Even when a system collects shopping site data automatically, humans initially enter the information. A human clicks various items, adds them to a shopping cart, specifies characteristics such as size and quantity, and then checks out. Later, after the sale, the human gives the shopping experience, product, and delivery method a rating and makes comments. In short, every shopping experience becomes a data collection exercise as well. Many data sources today rely on input gathered from human sources. Humans also provide manual inputs. You call or go into an office somewhere to make an appointment with a professional. A receptionist then gathers information from you that's needed for the appointment. This manually collected data eventually ends up in a database somewhere for analysis purposes. Data is also collected from sensors. Then these sensors can take almost from any form. For example, many organizations base physical data collections, such as the number of people viewing an object in a window or cell phone detection. Facial recognition software could potentially detect repeat customers as well. However, sensors can create datasets from almost anything. The Weather Service relies on datasets created by sensors that monitor environmental conditions such as rain, temperature, humidity, and cloud coverage. Robotic monitoring systems help correct small flaws in robotic operation by constantly analyzing data collected by monitoring sensors. A sensor combined with a small AI application could tell you when your dinner is cooked to perfection tonight. The sensor collects data, but the AI application uses rules to help define when a food is properly cooked. Now we can continue with obtaining reliable data. The word reliable seems so easy to define, yet so hard to implement. Something is reliable when the results it produces are both expected and consistent. A reliable data source produces mundane data that contains no surprises. No one is shocked in at the least by the outcome. Depending on your perspective, it could actually be a good thing that most people aren't yawning and then falling asleep when reviewing data. The surprises make the data worth analyzing and reviewing. Consistently, data has an aspect of duality. We want reliable, mundane, fully anticipated data that simply confirms what we already know, but the unexpected is what makes collecting the data useful in the first place. Still, you don't want data that is so far out of the ordinary that it becomes almost frightening to review. Balance needs to be maintained when obtaining data. The data must fit within certain limits, and it must also meet the specific criteria of truth, value, and the data must also come at expected intervals, and all the fields of the incoming data record must be complete. To some extent, data security also affects data reliability. Data consistency comes in several forms. When the data arrives, you can ensure that it falls within expected ranges and appears in a particular form. However, after you store the data, the reliability can decrease unless you ensure the data remains in the expected form. And entity fiddling with the data affects reliability, making the data suspect and potentially unusable for analysis later. Now let's focus on making human input more reliable. Humans make mistakes, so we should focus on that we get rid of our mistakes. Many application designs assume that humans somehow won't make mistakes at all. And the design expects that everyone will simply follow the rules. Unfortunately, the vast majority of users are guaranteed to not even read the rules, because most humans are also lazy or too pressed for time when it comes to doing things that don't really help them directly. consider the entry of a state into a form. If you provide just a text field, some users might input the entire state name, such as Kansas. Of course, some users will make a typo or capitalization errors, or even come up with, instead of Kansas, so Kansas, KANZUZ, or KANSUS, and so forth. Setting these errors aside, people and organizations also have various approaches to performing tasks. So in this way, for example, a drop-down menu would help to limit choices and not to make any mistakes. Drop-down list boxes work well for an amazing array of data inputs, and using them ensures that human input into those fields become extremely reliable, because the human has no choice but to use one of the default entries. Of course, the human can always choose the incorrect entry, which is where double checks come into play. Some newer applications compare the zip code to the city and the state entries to see whether they match. When they don't match, the user is asked again to provide the correct input. This double check verges on being annoying, but the user is unlikely to see it often, so it shouldn't become too annoying. So automatically correct a number of formats as well. Even with cross checks and static entries, humans still have plenty of rooms making mistakes. For example, entering numbers can be problematic. When user needs to enter 2.00, you might see 2 or 2.0 or 2 point, or any of the variety of other entries. Fortunately, parsing, so here we go, input parsing and reformatting. Parsing and reformatting fixes the problem, and you can perform this task automatically without the user's help. Reformatting doesn't correct an errant numeric input always. You can partially mitigate such errors by including range check. Here you see range check. And the legitimate way to show that a customer is returning the 5 bars of soap is to process the return. Okay, not a sale. Now, let's continue with using automated data collection. Oh, yes, here we go. So we see here pros and cons of automation, but let's first check. So some people think that automated data collection solves all the human input issues associated with datasets. In fact, automated data collection does provide a number of benefits. So see, better consistency and reliability, improved reliability as well, of course. Then lower probability of missing data, then enhanced accuracy, you see here, and reduced variance of factors like timed inputs. Unfortunately, to say that automated data collection solves every issue is simply incorrect. Automated data collection still relies on sensors, applications, and computer hardware designed by humans that provide access only to the data that humans decide to allow. because of the limits that humans place on the characteristics of automated data collection, the outcome often provides less helpful information than hoped for by the designers. Consequently, automated data collection is in a constant state or flux as designers try to solve the input issues. Automated data collection also suffers from both software and hardware errors present in any computing system, but with a higher potential for soft issues, you see here, which arise when the system is apparently working but isn't providing the desired results than other kinds of computer-based setups. When a system works, the reliability of the input far exceeds human abilities. However, when soft issues occur, the system often fails to recognize as a human might that a problem exists, and therefore the dataset could end up containing more mediocre or even bad data. We can now continue with collecting data ethically. So let's see that. So for some people, anything that appears on the internet is automatically considered public domain, including people's faces and all their personal information. The fact is that you should consider everything as being copyrighted and unavailable for use in a public domain manner to use data safely. Even people who realize that material is copyrighted often fall back on fair use principles. Fair use can be quite a tricky subject that was so be careful with that. The problem with considering fair use alone is that it's also essential to consider a person's right to privacy, and consistently it shouldn't surprise anyone that a major ruckus arose when companies started scrapping images of people wearing masks from the internet without obtaining any permission whatsoever. In fact, Facebook sued and lost lawsuit over its misuse of user data. The right to privacy has also created new industry for making person's face less useful to companies that are determined to get free data without permission by using any means possible. The fact is, no matter where you stand on the free use issue, you still need to consider the ethical use of data that you obtain, no matter what the source might be. Here are some considerations to keep in mind as you collect personal data ethically. So the first one is obtaining permission. Some research requires you to be able to identify persons used within a dataset. Going out and grabbing personally identifiable information, so personally identifiable information, PII, isn't a good way to gather data. For one thing, you can't be sure that the information is either complete or correct, so any analysis you perform is suspect. For another thing, you could encounter the messy and costly consequences of legal actions. The best way to obtain data with PII, so personally identifiable information, is to ask for permission. Using sanitization techniques. Data sanitization involves removing personal information, such as name address, phone number, and ID from a dataset so that identifying a particular individual in a dataset becomes impossible. In addition to text and dataset variables, you must consider every kind of data. For example, if you're working with collections of photos, it is paramount that you take steps to blur faces and remove curve plates from your images. The next one is avoiding inference. So when collecting data, some users refuse to share personally identifiable information, so PII, such as gender and age. Some people recommend you infer this information when a user's picture or other information is available. Unfortunately, names associated with one gender in a particular culture may be assigned to another gender in another cultures. The problem with age inference is even more profound. For example, machine learning algorithm will likely infer the wrong age for an albino, which can affect as many as 1 in 3,000 individuals, depending on the part of the world the data comes from. And the last one here, avoiding generalization. Many fields of study try to incorrectly apply statistics and machine learning outcomes, with the result that the individual or individuals end up being mistreated in some manner. So it is essential to remember that statistics apply to groups, not to individuals. So we can now continue with manicuring the data. Some people use the term manipulating when speaking about data, giving the impression that the data is somehow changed in an unscrupulous or devious manner. Perhaps a better term is manicuring, which makes the data well shaped and lovely. No matter which term you use, so manipulating all the data or manicuring the data refers to the same data manipulation. So to get something from a data, you must manicure it to meet specific needs, and we talk about it now this time here. Dealing with missing data is the first part. To answer a given question correctly, you must have all the facts. You can guess the answer to a question without all the facts, but then the answer is just as likely to be wrong as correct. Often, someone makes a decision essentially answering a question without all the facts is said to jump to a conclusion. When analyzing data, you have probably jumped to more conclusions than you think because of missing data. A data record or one entry in a dataset, so which is all the data, consists of fields that contain facts used to answer a question. Each field contains a single kind of data that addresses a single fact. If that field is empty, you don't have the data you need to answer the question using the particular data record. As part of the process of dealing with missing data, you must know that the data is missing. Identifying that your data set is missing information can be quite difficult because it requires you to look at the data at a low level, something that most people are unprepared to do, and that is time consuming even if you do have the required skills. Often your first clue that data is missing is the preposterous answers that your questions elicit from the algorithm and associated dataset. Now, when the algorithm is the right one to use, the dataset must be at fault. So here are some issues to consider. The first one is essential data missing. A problem can occur when a data collection process lacks all the data necessary to answer a particular question. Then some data missing. Okay, here we go. Right? Exactly, here we go. Less damaged fields can have data missing in one of the two ways. Here we go. Two types. So randomly missing data is often the result of human or sensor error. Fixing randomly missing data is easiest. You can use a simple median or average value as a replacement. And sequentially missing data occurs during some type of generalized failure. Fixing sequentially missing data is significantly harder, if not impossible, because you lack any surrounding data in which to base any sort of kind of guessing. If you can find the cause of missing data, you can sometimes reconstruct it as well. Now, considering data misalignment. Data might exist for each of the data records in a dataset, but it might not align with other data in other datasets your own. So let's take the example of numeric data in a field. In one dataset might be a floating point, so 1.3325, something like that, with a decimal point. But in another type of the dataset, it could be an integer dataset, so without point something. Then before you can combine the two datasets, the fields must contain the same type of data. And then all sorts of other kinds of misalignment can occur. For example, date fields are wrongly formatted, time fields are wrongly formatted, or even names are wrongly formatted. So one dataset may treat first and last names as single field, while another dataset might use separate fields for first and last names. The answer is to change all datasets to use a single field, or to change them all to use separate fields for first and last names. Unfortunately, many misalignments in data content are harder to figure out. Before you give up, you could consider a few things here. Calculate the missing data from other data you can access. Then the next one is locate the missing data in other dataset. Combine the datasets to create a whole that provides consistent data or consistent fields. And then the next one is collect additional data from various sources to fill in the missing data. And then redefine your questions so that you no longer need the missing data. We can jump to the next topic in manipulating the data itself. Separating useful data. Some organizations' leaders are of the opinion that they can never have too much data, but And excess of data becomes as much a problem as not enough data. To solve problems efficiently, an AI requires just enough data. Defining the question that you want to answer concisely and clearly helps, as does using the correct algorithm or algorithm ensemble. Of course, the major problems with having too much data are that finding the solution takes longer, and sometimes you get confusing results because you can't see the forest from the trees as well. So if there's a tree, it happens sometimes. I mean, wear my glasses in this way, right? Where are my glasses? Have you seen my glasses? Oh, they are here. The same happens again and again as well. Now, let's get back to the goal. As part of creating a dataset, you need, for analysis, you make a copy of the original data rather than modify it. That's the golden rule. Now, creating the right data output for analysis can require a number of tries because you may find that the output doesn't meet your needs. The point is, so the focus is to create a dataset that contains only the data needed for analysis. But keep in mind that the data may need specific kinds of pruning to ensure the desired output.